Right now, this moment you are inside of has never moved. It has never become past. According to one of the strangest equations in modern physics, you are not living through this moment. You are a single page in an infinite library, and every other page of your life, every breath you have ever taken, every breath you will ever take, exists exactly as you do now, frozen, whole, present. In 1955, Albert Einstein wrote a letter saying the separation between past, present and future is, for believing physicists, only the meaning of an illusion. He meant the mathematics of relativity already implies it. In 1967, Wheeler-DeWitt and John Wheeler wrote what was meant to be the quantum description of the universe. The equation worked. It also deleted time. The variable that should describe change was simply not there. Then Julian Barbour asked what would happen if you believed the equation as an account of reality. The result is Platonia, a static landscape of every possible now, all existing at once. No flow, no passage, no tomorrow approaching. By the end of this video, you will understand how Einstein's equations make the block universe inevitable. You will understand how the Wheeler-DeWitt equation erased time. You will understand what Barbour's Platonia, Time Capsules and Janus Point actually claim. You will see why the entropy of the early universe is the most improbable number in physics. And you will see where the evidence really points. If you find value in explorations like this, in understanding the deep puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Begin with the equation that started the trouble. Einstein's general theory of relativity is one of the most experimentally validated frameworks ever produced. It is written in a single line of geometry. G mu nu plus lambda G mu nu equals 8 pi g over c to the fourth T mu nu. The Einstein tensor on the left describes the curvature of space-time. The stress-energy tensor on the right describes the matter and energy that lives inside it. Lambda, the cosmological constant, sits between them, a number so small and so finely set that physicists still cannot say where it comes from. The equation tells us how matter curves geometry, and how geometry tells matter where to go. It also tells us something stranger. In the geometry Einstein wrote down, time is not a flow. Time is a direction in a four-dimensional manifold. 3 of those dimensions are space. The fourth is time. Together they form a single fabric, space-time. And an event in the universe is not a happening, but a location, a point on that fabric. The dinosaurs are not gone. They are at a particular space-time coordinate. Your great-grandchildren are not waiting to arrive. They are at a different coordinate. And every observer who has ever existed, or ever will exist, sits at a single point on this same continuous block. This is what philosophers of physics call eternalism, or, more vividly, the block universe. The block universe is not a fringe interpretation. It is the most natural reading of relativity. In 1905, with special relativity, Einstein already showed that simultaneity is observer-dependent. What is happening right now on Mars depends on how fast you are moving relative to Mars. Different observers slice the four-dimensional fabric into present and past and future differently. No slicing is more correct than any other. Hermann Minkowski, in 1908, gave this picture its geometry. He fused space and time into the space-time continuum and remarked that henceforth space by itself and time by itself were doomed to fade away. In 1915, with general relativity, Einstein extended the idea to gravity. There is no longer a universal clock ticking behind the universe. Each world line carries its own proper time. The global positioning system, which you carry in your phone, only works because of this. The atomic clocks on those satellites tick at a different rate than the ones on the ground, by about 38 microseconds per day, and engineers correct for this every second. Relativity is not philosophy. It is timekeeping infrastructure. Without it, your turn-by-turn directions would drift by miles within hours. There is a price the engineers do not pay. The price is paid by the physicist who asks what the equations mean. Picture a sheet of paper. Draw your own life on it. The infant version of you on the left. The version of you watching this video in the middle. The version of you taking your last breath on the right. All on the same sheet, all present at once. The block universe says that sheet is real. The you on the left is not gone. The you on the right is not waiting. The flow you feel between them is something else, not a property of the sheet itself. Albert Einstein, the man whose mathematics made this picture inevitable, wrote a letter in March of 1955 to the family of his oldest friend, Michel Bessot, who had just died. In that letter, he said this: "For us believing physicists, the distinction between past, present, and future has only the meaning of an illusion, however persistent." He died 1 month later. Think about the precision of what he was saying. He was not telling a grieving family that the dead are gone. He was telling them that, on the deepest reading of relativity, the dead are not gone. They are at a different coordinate of a single block that all of reality occupies. Whether he believed this as comfort or as cold mathematics, the equations he wrote down made it the natural reading. This is the first claim we are going to weigh. We will return to whether the block universe really removes time or whether it merely reframes it. We will return to whether Einstein's illusion is the kind of illusion materialism can explain or the kind that points somewhere else. For now, hold the picture. 3 dimensions of space, 1 dimension of time, a 4-dimensional block. Every moment of your life laid out like the frames of a film strip. Every frame as real as every other. Now we add quantum mechanics, and the picture breaks. In 1967, the American physicist Wheeler-DeWitt, joined by John Archibald Wheeler, the same Wheeler who later coined the phrase black hole, attempted to write down a quantum description of the entire universe. They were applying the techniques of canonical quantization to the constraints of general relativity. The work built on earlier formalism by Arnovit, Deser and Meissner, the ADM decomposition, which had taken Einstein's 4-dimensional geometry and split it into a stack of 3-dimensional spatial slices, evolving in time according to a Hamiltonian function. What Wheeler and DeWitt produced was a single equation. Speak it. H hat applied to capital psi equals 0. The Hamiltonian operator acting on the wave functional of the entire universe gives 0. Written more fully, H hat psi of H sub ij, phi equals 0, where H is the three-dimensional spatial geometry and phi is whatever matter fields you put in it. This is the Wheeler-DeWitt equation. It is the quantum gravity analogue of Schrödinger's equation for the universe. And there is no time in it. Look at it. Compare it to ordinary quantum mechanics. The Schrödinger equation has a partial derivative with respect to time on its left side. It says the wave function changes as time advances. The Wheeler-DeWitt equation has no such term. The equation does not describe a wave function that evolves. It describes a wave function that simply is. The technical name for this is the Hamiltonian constraint. In any theory invariant under reparametrization of time, that is, in any theory where the choice of time coordinate is gauge, the total Hamiltonian must vanish. Paul Dirac noticed this in the 1930s when he developed the formalism of constrained systems. The cosmologists who quantized gravity inherited the conclusion. In a universally covariant theory, the Hamiltonian, the operator that ordinarily generates time evolution, is identically 0. Apply it to a state and you get 0. There is nothing left to drive change. To see what this means, picture an ordinary piece of machinery, a motor with a crankshaft. The crankshaft has a drive. The drive rotates because something turns it, an engine, a hand crank, a falling weight on a string. Now picture a motor whose drive is wired, by design, never to turn. Not because the engine is off, because there is no engine, only an enforced equation that says the rotation is 0. The crankshaft is what it is. The flywheel is what it is. The pistons are in whatever positions they are in. Nothing rotates because the equation that should describe rotation says 0. That is the Wheeler-DeWitt situation. The wave function of the universe contains the configurations. The equation that should evolve them through time enforces instead that there is no evolution. The state simply is. Compare this to ordinary quantum mechanics. There, the Schrödinger equation does have a time-dependent term. IH bar times the partial derivative of the wave function with respect to t, equal to the Hamiltonian acting on the wave function. The time parameter is external to the system. It is supplied by a clock outside the quantum state. When you do an experiment in a laboratory, the clock is on the wall. The clock is not part of what you are measuring. The time variable in the Schrödinger equation is provided by the laboratory, not by the system. In quantum cosmology, there is no laboratory, and no wall, and no external clock. The whole universe is the system. There is nothing outside it from which a time coordinate could come. Wheeler-DeWitt is what you get when you honestly ask what happens when the system includes everything. Time, as an external parameter, is no longer available. So the equation drops it. And what you have left is a constraint, not an evolution equation. H hat psi equals 0, not because the Hamiltonian is broken, but because there is no longer any outside from which to set the clock. This is not a peripheral problem. It is widely taught. In 1991, Chris Isham and Carol Rovelli each wrote review articles on the problem of time in quantum gravity, both of which have been cited thousands of times. Neither paper offered a solution. Each laid out the conceptual landscape. Each documented the failures of the existing approaches. 3 decades later, the same review article could be written, with updated references, and would say roughly the same thing. The problem of time is not the kind of problem that the field has been embarrassed about. It is the kind of problem that the field has openly catalogued decade after decade, while continuing to do other work. The technical name for the situation, again, is the frozen formalism. The universe in this formulation is a stationary wave function. The cosmos does not run, it stands. The wave function superposes all possible three-dimensional geometries, every possible arrangement of curvature, of matter, of fields, and weights them with amplitudes. But it does not march any of them forward into the next moment. This is the problem of time in quantum gravity, and it is not a minor technical detail. It is a central, recognized, openly admitted puzzle in the foundations of physics. Chris Isham and Carol Rovelli, two of the field's most precise reviewers, surveyed the situation in the early 1990s and could not identify a consensus solution. 3 decades later, there still is none. What does it mean that the most ambitious equation in modern physics, the equation that should describe the universe as a whole, predicts that the universe does not evolve? There are responses, of course. Physicists have proposed that time emerges from inside the wave function rather than from outside it. The Page-Wootters mechanism, proposed by Don Page and William Wootters in 1983, suggests that if you split the universe into a subsystem you call a clock, and the rest, the correlations between them produce an effective time evolution for the rest, even though the universe as a whole is in a stationary state. The Connes-Rovelli thermal time hypothesis from 1994 defines a flow from the statistical operator of the universe using modular theory. These proposals exist. None has been promoted to consensus. The mainstream view is, with characteristic honesty, that the meaning of time in quantum gravity is unsettled. The Wheeler-DeWitt equation is what the standard procedure produces when you apply quantum mechanics to gravity. The standard procedure produces a timeless equation. The standard interpretation does not know what to do with it. This is the second claim we are going to weigh. We will return to the Wheeler-DeWitt equation when we examine whether Julian Barbour is reading too much into it, or whether he is reading exactly the right thing. For now, hold both pictures together. From relativity, a 4-dimensional block in which all moments of your life are coordinates on a single fabric. From quantum gravity, a wave function of the universe in which time, as a fundamental variable simply does not appear. These are not interpretations imposed on the equations by philosophers. They are what the equations say when you let them speak. Now we cross into Mach. The German-Austrian physicist Ernst Mach, in 1893, criticized Isaac Newton's idea of absolute space and absolute time. Newton had imagined an invisible, unchanging container, a stage on which the universe plays out. Mach insisted that this container was a fiction. Only the relative positions of bodies matter. There is no absolute space, because nothing distinguishes a stationary frame from a moving one, except the matter you can use as a reference. There is no absolute time, because nothing distinguishes one moment from another, except the relations between things. This view came to be called Mach's principle. Einstein took it seriously when constructing general relativity, although whether GR actually implements Mach's idea or only partially honors it is itself contested. What Mach said clearly is that physics ought to be purely relational. The laws should be written in terms of distances and angles and configurations, not in terms of a hidden background clock or ruler. In 1982, Julian Barbour and Bruno Bertotti, Barbour, an independent scholar who had stepped outside academia to think slowly, and Bertotti, a relativist at the University of Pavia, published a paper that took Mach's principle as far as anyone had taken it. They wrote a Machian reformulation of Newtonian mechanics. In their formulation, there is no background time. The dynamics is defined entirely on a configuration space, a mathematical space whose points are arrangements of n particles, with global translations and rotations quotiented out, so that only intrinsic configurations remain. They produced something called a Jacobi action. The action is a function of paths through configuration space. Extremizing it gives the same trajectories Newton's laws give. But time is not put in by hand. Time emerges as a measure of progress along the path, what they called ephemeris time, an internal counter derived from the system itself. This was a proof of principle. Classical mechanics can be written without absolute time and recover all the predictions of Newton. The container is not necessary. What is necessary is the configuration space and the action that defines paths across it. Now, Barbour did what Mach never did. He took this idea that physics is really about a timeless configuration space and asked what kind of space it would be if you extended it to the whole universe. Not 3 particles, not 300, the whole cosmos. He gave that space a name. He called it Platonia. The name is borrowed from Plato. Plato's realm of forms was a timeless landscape of ideal shapes, the eternal templates of which our physical world is a shadow. Barbour's Platonia is something analogous, but mathematically literal. It is the configuration space of all possible spatial arrangements of the universe. Every possible 3-dimensional geometry, every possible distribution of matter, quotiented by the symmetries that should not matter physically. Each point of Platonia is a complete, simultaneous arrangement of the entire cosmos. Barbour calls each such arrangement and now. Picture this. Imagine an unfathomably high-dimensional landscape. Not a hill, but a country. Not a country, but a manifold. Every point on it is a complete state of the universe at an instant. One point is the universe right now, with these galaxies in these positions and you in this chair. Another point, somewhere far away in the landscape, is the universe 10 years ago. Another point is the universe at the moment of the dinosaurs. Another is the universe 10 years from now. None of these points is before or after the others. They are just points on the same landscape, and the landscape exists. This is Platonia. What does it mean that, if Barbour is right, you have not travelled from yesterday to today? Yesterday is a point in Platonia. Today is a different point. The brain that you call yourself is a different physical configuration at each point. Nothing has moved. Nothing has passed. There is no path that is actually being traversed. Every now simply is. We will return to whether this is even coherent. We will return to whether something has to traverse the path or whether the structure of the path is enough. For now, just sit with the picture. A landscape of all possible instants of the universe. None of them happening, all of them present. We have the block, universe of relativity, in which all moments are coordinates on a four-dimensional fabric. We have the frozen formalism of quantum gravity, in which the wave function of the universe is stationary and time does not appear in the master equation. We have Mach's principle and the Barbour-Bertozzi-Jacobi action, which show that classical mechanics can be written without any background time at all. And we have Platonia, a configuration space of every possible now, none of which becomes any other. What does it mean that every major foundational theory of physics, when pressed for what time really is, returns the answer that it is not what it appears to be? We will return to this. Now, let us go deeper. If Platonia is the landscape of every possible instant of the universe, the first question is the obvious one. Why does it feel as if we are moving through it? Julian Barbour's answer is one of the most original ideas in 20th century physics. He introduced it most fully in his 1999 book, The End of Time, and he sharpened it in his 2020 book, The Janus Point. The answer has a name. He calls it the Time Capsule. A time capsule is a particular kind of now. It is a configuration of the universe whose internal structure encodes the appearance of a consistent past. It contains, all at once, the rocks in their strata, the fossils inside the rocks, the photographs in the album, the entries in the ship's logbook, the neurons in the brain holding what feel like memories. None of these records were laid down by a process. The now in which they appear is not the end point of a journey. It is simply a particular point in Platonia, and that point happens to be one in which all of these traces are mutually consistent with a story we would call its past. Consider what this implies. The photograph on your wall of a moment from your wedding was not taken. It was never taken. There is no earlier now from which the camera click propagated forward into this now. There is only this now in which the photograph exists. The chemistry of the print is in a particular state. The synapses in your head are configured in a way you experience as remembering. All of these features happen to point internally at a self-consistent story. Barbour calls a configuration like this a time capsule because it carries inside it everything we ordinarily attribute to history. The geologist deduces the age of the Earth from the layered records of rocks. The archaeologist deduces the existence of vanished civilizations from the patterns of post holes and pottery shards. The neuroscientist tells us memories are physical patterns in the brain. In Barbour's reading, every one of these inferences is correct in a sense and wrong in another. The records exist. The story they tell is internally self-consistent. But there is no underlying history that the records record. The records and the brain that reads them are one piece of one now. What does it mean that if Barbour is right, your sense that you remember your childhood is not a memory of an earlier state of the world, but a current property of your current configuration? Picture it this way. Think about a freeze frame from a film, a single still image taken from somewhere in the middle of the movie. If the still is sufficiently detailed, if it shows the wear on the actor's costume, the lit cigarette in the ashtray, the look in the actor's eyes, you can infer the story that preceded the frame. But the story you infer is not in the frame. It is a reconstruction your mind builds from the frame's internal evidence. Now imagine that there is no film. There is only the still. The story you reconstruct is real in the sense that the frame really points to it. It is not real in the sense that no scene preceding the frame was ever shot. Barbour wants you to consider that the universe might be like this. Each now is a freeze frame so internally detailed that everyone inside it reconstructs the same story. They call that story the past. But the story is not a sequence of earlier nows that this now is the latest in. The story is a property of the current configuration. The now is a time capsule of a history that, in Barbour's picture, has no separate existence from the structure of the capsule itself. This is one of the most counterintuitive ideas in modern physics. Stay with it. It will matter when we get to part 3. Now connect time capsules to the Wheeler-DeWitt equation. Recall what that equation says. The wave function of the universe, capital Psi, defined on the space of all possible three-dimensional geometries and matter configurations, must satisfy h hat psi equals 0. There is no evolution. There are only amplitudes assigned to different points in this space. Barbour's central conjecture is that the structure of these amplitudes is biased toward time capsules. The mathematics of the Wheeler-DeWitt equation, he argues, distributes more probability over configurations whose internal records mutually agree than over configurations whose internal records are noise. The static landscape is not flat. It has structure. and the structure favours precisely the kind of now in which there are brains holding consistent memories and rocks holding consistent fossils. This is conjectural. Barbour says so himself. The Wheeler-DeWitt equation is famously hard to solve, riddled with operator ordering ambiguities, and the precise distribution of probability over configuration space has not been computed in general. The conjecture is mathematically motivated. The action whose extrema define Platonia's geodesics, the Jacobi-type action Barbour and Bertotti wrote down, is structured in a way that, in the model cases studied, channels the probability current toward more highly correlated configurations. The static landscape, in other words, sculpts a path of high likelihood through configurations rich in internal consistency. You and I sit at one such point. The brain, reading these words, is configured as part of a now in which the floor beneath you, the chair behind you, the words you remember from a moment ago, and the words you are about to read are all woven into a single, mutually consistent structure. Barbour says that this is not a coincidence. The probability distribution over Platonia funnels reality, so to speak, into points of high coherence. What does it mean that the explanation for why we remember a coherent past is, on this view, not that there was a past, but that the static probability distribution over a timeless landscape happens to favour configurations that look as if there was one? Hold the answer for part 3. Move on. Take a concrete example. Consider the lunar rocks that the astronauts of the Apollo missions, Apollo 11, 12, 14, 15, 16 and 17, between 1969 and 1972, brought back to Earth. Roughly 382 kilograms of moon material, about 842 pounds, scattered across labs around the world. Geochemists subjected those rocks to isotopic analysis. They counted the ratios of uranium and lead, of potassium and argon, of rubidium and strontium. The numbers came out the same in every independent lab, roughly 4.5 billion years old. The Moon, the rocks tell us, formed billions of years before the first cellular life appeared on Earth. On the standard reading, this dating is testimony of an actual history. The rocks are old because they have been around a long time. The isotopes have decayed because nuclei have actually been ticking down through the years. On Barbour's reading, the rocks are old in a different sense. The rocks are configurations of nuclei whose populations of isotopes are at certain ratios. Ratios that, by the laws of physics, are mutually consistent with a story of 4.5 billion years of decay. The story is not behind the rocks. The story is encoded in the rocks. The current configuration of the universe is one in which the lunar rocks have these particular ratios, and the brains of geochemists are configured to read those ratios and to call the result an age. The story they extract is internally consistent. It is also, in Barbour's framework, not a story of a process. It is a description of a present pattern. What does it mean that the same physical observations, the same isotopic ratios, the same calculations, the same conclusions in laboratory journals, can be explained either as testimony of a real past or as the structural features of a single static present, and that no observation distinguishes between the two interpretations. The interpretations are observationally equivalent. They differ only at the level of metaphysical commitment. Barbour's commitment, taken seriously, is that the second description is the more economical. There is one configuration with its internal structure. There is no second thing, no separate history that the rocks are testifying to. The structure is sufficient. We will return in Part 3 to whether the structure is also self-sufficient, whether the existence of this remarkable now, full of mutually consistent records read by brains configured to read them, requires an explanation external to the static landscape that contains it. Barbour did not stop at static time capsules. In the late 1990s, and increasingly across the next 25 years, working with Enrique Gomez, Tim Kozlowski, Flavio Mercati, Sean Gribb, and a small but persistent network of collaborators, he developed what is now called shape dynamics. Shape dynamics is a reformulation of general relativity that aims to take Mach's principle to its limit. In standard general relativity, the gauge symmetry is refoliation invariance. You can slice spacetime into instants in many different ways, and the physics is invariant under your choice. Shape dynamics trades this symmetry for a different one. It is invariant under local scale transformations, what mathematicians call conformal transformations. Under a conformal transformation, the overall size of a configuration can change at every point, but its angles and ratios are preserved. The trade is elegant. In shape dynamics, what is fundamental is not the four-dimensional spacetime metric, but the three-dimensional shape, the conformal class of the spatial geometry. Two configurations that differ only by a smooth rescaling of distances are considered the same physical state. Only the intrinsic shape of space matters, only the ratios, only the geometry stripped of any absolute scale. Picture two triangles. One is small, the other large. Both have the same angles at their corners. By Euclidean reasoning, they are similar, same shape, different size. In shape dynamics, similar configurations are identical. The universe is described not by a metric you can plug a ruler into, but by a sequence of shapes, where each shape is the universe's conformal geometry at a moment. The remarkable result, established mostly by Gomez, Gribb, Kozlowski and their colleagues in a series of papers between 2010 and the present, is that shape dynamics is mathematically equivalent to general relativity in a particular gauge, the constant mean curvature gauge. Whatever Einstein's equations predict, in spacetimes that admit a CMC foliation, shape dynamics also predicts. They are dual. The framing is different. In general relativity, the equations describe a four-dimensional block of spacetime. In shape dynamics, the equations describe an evolving sequence of three-dimensional shapes. The time in shape dynamics is not a coordinate of an external manifold, it is an internal counter derived from the changing geometry, much as in the Barbour-Bertotti-Jacobi action. Shape dynamics is a minority research program. It is not standard. Many relativists are skeptical that the conformal symmetry is the right organizing principle, or that the equivalence to GR is as clean as its proponents claim, especially for non-compact spacetimes or with the inclusion of matter fields. The debate is real. The framework exists. It is mathematically consistent in the cases that have been studied, and it gives Barbour what he needs to make Platonia not just a philosophical proposal, but a concrete physical theory. The configuration space he calls Platonia is, in shape dynamics, the space of conformal three geometries, the space of all possible shapes the universe could have, modulo size. The points of Platonia are the conformal three geometries. The dynamics, if you want to call it that, is the geodesic flow on this space, derived from a Jacobi-type action. Each geodesic corresponds to a classical history of the universe. Quantize the theory and you get a wave functional on the same space, satisfying a constraint analogous to the Wheeler-DeWitt equation. The whole apparatus closes. You have a self-contained physical theory in which time, in any absolute sense, never appears. What does it mean that the most thoroughly Machian formulation of relativity available, the one that takes the principle of only relations matter to its limit, produces a theory in which time as a flow is removed by construction? Move on. Now to one of Barbour's most striking late ideas. The Janus Point cosmology, developed in collaboration with Tim Kozlowski and Flavio Mercati and published in 2014 and refined the Janus Point in 2020. The setup is this. Consider a model universe, a system of n gravitating particles in Newtonian gravity, or its shape dynamics analog. Define a function on its configuration space called the complexity. The complexity, in essence, measures how clumped or how spread out the configuration is, how much structure it contains. There is a precise definition involving the ratio of the center of mass moment of inertia to the mean separation, but you do not need it. The key point is this. If you let the universe evolve from a generic starting configuration, the complexity does not behave monotonically. It has a global minimum. That minimum is the Janus point. At the Janus point, the universe is at its smoothest, simplest, least clumped state. Move away from the Janus point in either direction along the evolution, and the complexity grows. Galaxies form, structure increases, records accumulate. From any vantage point on either side of the Janus point, the past, the direction toward less complexity, is in the direction of the Janus point itself. The future, the direction toward more complexity, is in the direction away from it. Here is the consequence. In a universe organized this way, two arrows of time radiate outward from the Janus point. Two histories, two universes, if you like, sharing a single minimum complexity origin. The thermodynamic arrow on one side points away from the Janus point. The thermodynamic arrow on the other side also points away from the Janus Point, but in the opposite direction. The Janus Point cosmology offers a startling answer to the question of why the universe started in such a low entropy state. It did not start in a low entropy state. The Janus Point, the minimum of complexity, is just a generic feature of the evolution of any system of this type. If you stand on one side of it and look back, you see what looks like a special, smooth, ordered beginning. But that beginning is not specially configured. It is a natural geometric feature of the configuration space. The arrow of time is not imposed by a magical past hypothesis. It is what you get for free when complexity has a minimum. And the entropy on the other side of the Janus Point grows just as much in the other direction, populating a counter-universe whose own inhabitants, if any, would call it their forward time, and would look at our universe through their past. What does it mean that the most successful timeless formulation of cosmology not only removes time as a fundamental variable, but also doubles it, produces two arrows of time as twin children of a single static landscape? We will return to whether this removes the need for a special initial condition or whether it only relocates it. For now, hold the picture. Now broaden the field. Barbour is not alone in claiming that fundamental physics has no place for time. Carlo Rovelli, the Italian physicist who co-founded the Loop quantum gravity research program, has argued for decades that time, in the sense of an external flowing parameter, is not present in our best theories. His version of relational quantum mechanics, formalized in the 1990s, treats the quantum state as describing relations between systems, not absolute properties of any one. The Connes-Rovelli thermal time hypothesis, published with the French mathematician Alain Connes in 1994, defines a time flow purely from the statistical operator of a quantum system, via Tomita-Takasaki modular theory. The thermal time is generated by the state itself, not by an external clock. Rovelli's recent popular book, The Order of Time, is essentially an extended argument that the experience of flowing time is an effect of the thermodynamic gradient in our particular corner of the cosmos, not a fundamental feature of nature. Don Page and William Wootters in 1983 proposed what is now called the Page-Wootters mechanism. They considered a universe in an energy eigenstate, a stationary Wheeler-DeWitt style state, and asked what happens if you split it into two subsystems, calling one the clock and the other the rest. They showed that the correlations between the two subsystems, projected onto a definite reading of the clock, give a wave function for the rest that satisfies an effective Schrödinger equation. Inside a fundamentally static universe, an internal observer who can read a clock sees an evolving wave function. Time, in this picture, emerges from entanglement. Bryce DeWitt himself, the original architect of the Wheeler-DeWitt equation, remarked half in joke that solving the equation was like being locked in a room with no doors. He knew what he had written. He knew that the equation, taken literally, said the universe does not change. He spent much of his career looking for the door that would let an effective time back in. The pattern is clear. Across multiple independent research programs in foundational physics, relativity itself, canonical quantum gravity, loop quantum gravity, shape dynamics, relational quantum mechanics, thermal time, Page-Wootters internal clock proposals, Barbour's Platonia, the conclusion keeps returning. Time, in the sense in which we ordinarily speak of it, is not a fundamental variable in the equations. It is something that has to be recovered. It is something that emerges or fails to emerge depending on the technique. And no consensus has been reached on how. What does it mean that the entire frontier of fundamental physics points away from time as a basic feature of reality? Now, connect this to a question we have been deferring. What is the block universe theory, and how does it relate to Platonia? The block universe theory, eternalism, is the philosophical position that past, present and future all equally exist. It takes relativity at face value. There is no objective now. All events are coordinates on a four-dimensional space-time. The difference between past and future is no more ontological than the difference between north and south. The block exists. We move through it from our limited perspective. From the perspective of the block itself, all is present. Eternalism dates back, in modern form, to Minkowski and Einstein. It has been defended in detail by philosophers including Hilary Putnam in a famous 1967 paper using the relativity of simultaneity to argue that past, present and future events must all be equally real. By the Dutch philosopher C.W. Rietdijk the year before, and more recently by Ted Sider, whose 1997 work formalized four-dimensionalism. The block universe is widely held in philosophy of physics as the default reading of relativity. Here is the crucial distinction. The block universe still has space-time. It still has a four-dimensional manifold. It still has a metric. There is still a continuous fabric on which events lie. Two events with time-like separation are still ordered. Causal structure is still preserved. The block has internal geometry. Platonia is something more radical. Platonia is not a four-dimensional space-time. Platonia is a configuration space, and the points of Platonia are entire three-dimensional configurations of the universe. There is no space-time connecting them. There is no between. Two nows are 2 points in the landscape. The landscape has its own intrinsic geometry, defined by the action, but there is no underlying space-time stitching the nows together. Picture it this way. The block universe is a film strip. Every frame is real, the strip is finite or infinite, but there is a strip. You can run your finger along it. Platonia is a library. Every now is a separate book on its shelves. There is no shelf running through all the books that says this book came before that one. The library has its own geometry, a notion of which books are nearby on which shelves, but no continuous timeline links them. Barbour's Platonia is, in this sense, a more extreme position than eternalism. Eternalism reduces time to a dimension. Platonia removes it entirely and replaces it with the static structure of a configuration space. What does it mean that the two most influential positions in the philosophy of physics in the 20th century, eternalism and Platonia, both deny that time flows and only differ in how much of space-time they admit? Hold this, we will return to it. One more thread before we end this section. The arrow of time. The standard story of the arrow of time, developed by Ludwig Boltzmann in the 1870s, says this: "The fundamental laws of physics are nearly time-symmetric. If you played a film of an isolated mechanical system backward, it would still obey the laws. But the universe, on a large scale, is asymmetric. The second law of thermodynamics says that entropy, the measure of disorder, tends to increase in time. Eggs scramble, they do not unscramble. Coffee cools, it does not spontaneously concentrate its heat. Rivers run downhill, they do not run uphill." Boltzmann's insight was that entropy increase is overwhelmingly probable, not metaphysically necessary. Among all the microscopic configurations of a system, those that look ordered to us are vanishingly rare. Those that look disordered are vastly more numerous. So, a typical evolution moves from ordered states to disordered ones simply by counting. S equals k Boltzmann log omega. Entropy is the logarithm of the number of microstates consistent with a given macrostate. Macrostates with large omega, many microscopic ways to realize them, are overwhelmingly more probable than macrostates with small omega. The arrow of time, in this view, is a statistical phenomenon. It points from low entropy past to high entropy future, because the past was extraordinarily low entropy, and we are statistically being dragged toward the bulk of phase space. This story has a price. It requires that the past was extraordinarily low entropy. This is the past hypothesis, the assumption that the universe began in a state of staggeringly improbable order. How improbable? Roger Penrose, the Oxford mathematical physicist, took this question seriously in a 1979 essay and a subsequent series of books. He estimated the phase-space volume of the actual early universe relative to a typical high-entropy universe of comparable energy content. The number he derived, and there has been no serious challenge to its order of magnitude, is approximately 1 part in 10 to the 10 to the 123rd. Let that number breathe. 10 to the 10 to the 123rd. The exponent is not 123. The exponent is 10 to the 123. To write the number out in ordinary digits, you would write a 1 followed by 10 to the 123rd zeros. That is more zeros than there are atoms in the observable universe, by, conservatively, 43 orders of magnitude. This is the level of fine-tuning Penrose says is required to explain why the universe began in a low-entropy state capable of supporting an arrow of time, evolution, structure, life, and your present moment of comprehending this sentence. Penrose has stated repeatedly that he does not know what to make of this number. He calls it the greatest puzzle in physics. He has proposed his own framework, conformal cyclic cosmology, but admits it is speculative and that the magnitude of the fine-tuning is not really reduced by it. Sean Carroll, the Caltech cosmologist, has written in his book From Eternity to Here that we have no theory of why the universe started in a low-entropy state. We assume it. We treat it as a boundary condition. We use it to derive the arrow of time we observe. But the assumption itself is uncaused on standard cosmology. The universe simply began in this incredibly improbable state. What does it mean that the entire structure of time we experience, the past, the future, the asymmetry between memory and anticipation, the existence of records and the absence of precognition, rests on a number of probability 1 in 10 to the 10 to the 123rd, which no current physics derives? Hold this. It is the most important number we will encounter, and the rest of this exploration turns on it. We have the time capsule, the proposal that each now in Platonia contains internal records that mimic a past without there having been a past. We have shape dynamics, the Machian reformulation of general relativity, in which only conformal shapes of space, not the four-dimensional space-time metric, are fundamental. We have the Janus Point, the geometric point in configuration space from which two thermodynamic arrows of time emerge as twin children of a single low-complexity origin. We have the Rovelli, Page-Wootters and Connes-Rovelli proposals, independent confirmations from outside Barbour's program that fundamental physics has no place for time as a basic variable, and that time, if anything, must emerge from inside the system rather than be imposed from outside. We have the block universe of relativity, with which Platonia overlaps, but which Platonia extends, to the point of removing space-time itself. And we have the past hypothesis, the 10 to the 10 to the 123rd improbability of the initial low-entropy state that underwrites the entire arrow of time. What does it mean that the deepest equations of physics describe a static reality? Yet the explanation for the arrow of time we experience requires an initial condition so improbable that the number describing it cannot be written in ordinary notation. This is what we have not yet asked. Now we examine. For the past hour, we have been laying out, as fairly as possible, what mainstream physics and its most radical timeless formulations claim. The block universe of Einstein, the Wheeler-DeWitt frozen formalism of canonical quantum gravity, Barbour's Platonia, time capsules, shape dynamics, the Janus Point, Rovelli's relational time, Page-Wootters' internal clocks, the past hypothesis. The claim that we will weigh in its strongest form is this: the deepest equations of physics describe a fundamentally timeless reality. Time is an illusion, or at most, an emergent statistical artifact. Therefore, so the claim continues, the question, why did the universe begin, is malformed. There is no beginning to explain. There is no flow to be driven. There is no creator required, because there is no creation event, because Platonia simply exists, complete, total, all nows present, with us inhabiting one of them. Let us hear this claim in its most disciplined version, and then test it. Some philosophers of physics, among them Bradford Scow and Ted Sider, have argued that taking eternalism seriously removes a great deal of the metaphysical work traditionally done by the concept of becoming. There is no coming into being, only being. And if there is no coming into being, there is no need to ask what brings the universe into being. The block, or the Platonia just is. Julian Barbour himself does not endorse a theological conclusion either way. He is, by his own description, agnostic. But the popular extension of his work and the philosophical use to which Platonia has been put by some materialists runs further. The claim, expanded, becomes this: if all nows exist statically, then questions of origin, design, and purpose dissolve. The universe is not created, it is not chosen. It is the brute given of an infinite configuration space. There is nothing left for an intelligent cause to do. This is the case we are examining. The first thing to notice is that this case mistakes structure for self-sufficiency. Consider very carefully what Platonia actually is. It is a high-dimensional configuration space, every point of which is a possible state of the universe, equipped with a specific action that gives it a geometry, a measure, and a structure that favors highly correlated configurations. It is not merely a set of possibilities. It is a structured manifold. The action is precisely specified. Barbour and Bertotti wrote it down explicitly. The conformal symmetry that defines which configurations count as identical is precisely specified. The quantization that gives the Wheeler-DeWitt wave functional is performed using a specific operator ordering and a specific gauge. Every one of these specifications could have been different. This is the cosmological argument restated in its strongest form. The chain of dependent specifications must terminate. We have the universe. We have the equations describing the universe. We now have, on Barbour's reading, a static landscape of all possible universes structured by a specific action and symmetry. Something specifies the action. Something specifies the symmetry. Something specifies the manifold over which the action is defined. To call Platonia self-existent is to refuse to ask what underlies the structure that makes it Platonia rather than some other static landscape with some other dynamics. The materialist response to this is usually one of two moves. Move 1. Declare that the action, the symmetry, and the manifold are just brute facts. Not explained, not explainable. Not the kind of thing for which an explanation is appropriate. The universe, or the configuration space in this case, simply has the structure it has, and the question why this structure is a category error. This is a stop. It is not an answer. It is the announcement that no answer will be given. Notice what it costs. The same move made by a theist would be ridiculed. If a theist said the existence of God is just a brute fact, not the kind of thing for which an explanation is appropriate, the materialist would, correctly, point out that this is not an argument but a refusal to engage. Yet the materialist makes exactly this move when pressed on the origin of Platonia's structure. The refusal is the same. The refusal does not become an argument by being made on behalf of a configuration space rather than on behalf of an intelligent cause. The principle of sufficient reason, the principle that contingent facts require an explanation outside themselves, does not respect the choice of metaphysical entity. If you are willing to apply it to God, you must apply it to Platonia. Move 2. Declare that Platonia is necessary, that no other configuration space is possible, and that therefore the question, why this rather than something else, does not arise. This move fails because nothing in the mathematics of configuration space requires uniqueness. We can write down many different configuration spaces with many different actions. Mathematicians do it routinely. Each of those configuration spaces would, on Barbour's interpretation, define a complete static universe. The materialist who claims that this configuration space, the one with the action that gives our particular Platonia, is necessary, owes an argument. No such argument exists in the literature. Barbour himself does not claim necessity. He claims the structure is what it is. What does it mean that the materialist defense of Platonia as ultimate reality requires either an admission of brute fact or a claim of necessity that the mathematics does not deliver? The second weight we must put on the scale is the past hypothesis. Recall what we established earlier. The arrow of time we experience, the asymmetry between memory and anticipation, the existence of records, the unidirectional growth of entropy in our cosmos, rests on the assumption that the universe began in a state of incomprehensible order. Roger Penrose estimated the improbability of that state on a uniform prior over phase space as 1 part in 10 to the 10 to the 123rd. This is a number whose exponent cannot be written in ordinary notation. Now consider what Barbour's Janus Point cosmology offers in response. The Janus Point provides a geometric mechanism by which what looks like a special low-entropy beginning is, in fact, a generic feature of any sufficiently rich configuration space, namely the global minimum of the complexity function. From either side of the Janus Point, you look back and you see a smooth, low-complexity past. The arrow of time falls out for free, the materialist tells us, without any need to fine-tune the initial conditions. This is a sophisticated response. It deserves a sophisticated examination. Notice what the Janus Point removes. It removes the need for a special initial condition imposed by hand at a specific moment in time. The configuration of the universe at any single now does not have to be tuned. The geometry of Platonia, taken as a whole, simply has a minimum of complexity, and we happen to be on one side of it. Now notice what the Janus Point does not remove. It does not remove the fine-tuning. It relocates it. The Janus Point exists because the configuration space, Platonia itself, has a particular structure. That structure includes a global minimum of complexity. Other configuration spaces with other actions would have different complexity functions, and not all of them would have a single global minimum. Many would have multiple local minima. Many would have no minimum at all. Many would have minima that do not correspond to low entropy states from which an arrow of time radiates. The Janus Point is a feature of this Platonia. The fine-tuning has not vanished. It has been pushed up one level, into the geometry of the configuration space itself. The question is no longer, why did the universe start in a state of 10 to the 10 to the 123rd improbability, the question is now, why does Platonia have a global complexity minimum of the kind from which arrows of time radiate, with the precise structure required for records, memories, and observers like us to occur? This is not a smaller question. It is the same question asked one floor higher. Think about what happens when a contractor proposes to fix a leak in a basement by raising the basement. He has moved the leak, he has not stopped it. What does it mean that the most ambitious attempt to remove the fine-tuning of the initial state of the universe achieves only the relocation of that fine-tuning into the structure of the configuration space that contains it? Hold this. Now to the third weight. The third weight is the multiverse move. It is the most popular response to fine-tuning in contemporary materialist cosmology, and Platonia has been used to dress it in a new costume. The reasoning broadly runs like this. If all nows exist, if every point of Platonia is just as real as every other, then there is no special improbability in our occupying a now with records, memories, and a coherent arrow of time. Among the vast landscape of Platonia, almost all configurations are noise. The only nows that contain observers are the ones rich enough in structure to support them. We find ourselves in such a now because no observer can find themselves in a now that does not support observers. The improbability evaporates as an anthropic selection effect, just as it does in standard multiverse cosmology. This argument has been advanced explicitly by Sean Carroll, Max Tegmark and others in the context of various multiverse frameworks. The application to Platonia is the natural extension. Let us test it. The first thing to notice is that the argument has the structure of a dilemma in disguise. To use the anthropic selection effect, you must have a measure on the space, a way of asking, given the structure of Platonia, what proportion of observers find themselves in a record-rich now? Without a measure, the argument is vacuous. You cannot say most observers are in noisy nows or almost no observers are in noisy nows without a way of weighting the points. What is the natural measure on Platonia? There is no agreed answer. Barbour himself has speculated that the Wheeler-DeWitt wave functional, properly interpreted, provides such a measure. But the interpretation of the wave functional is exactly the part of quantum gravity that has no consensus. There are at least 4 major proposed measures in the literature on quantum cosmology, and they give wildly different answers about which configurations are typical. Several of them lead to the so-called Boltzmann brane problem, the conclusion that, on a uniform measure, you are vastly more likely to be a momentarily arisen brane in an otherwise empty universe, with false memories of a coherent past, than you are to be an actual brane in a real history. This conclusion is so absurd, even on materialist grounds, that it is universally treated as a sign that the measure is wrong. The measure is wrong is not an answer. It is an admission that the materialist machinery used to diffuse fine-tuning depends on a measure that nobody knows how to define, and that, when filled in naively, predicts a universe wildly different from the one we actually observe. What does it mean that the materialist appeal to Platonia as an explanation for the apparent fine-tuning of our now depends on a measure on configuration space that, by mainstream physicists' own admission, either does not exist or, when proposed, contradicts observation. The fourth weight is the contingency of physical law itself. Notice what we have not yet asked. We have asked about the structure of Platonia. We have asked about the Janus Point. We have asked about the measure on configuration space. Behind all of these, sitting in plain sight, is something more fundamental. We have been writing equations the whole time. G mu nu plus lambda G mu nu equals 8 pi G over c to the fourth T mu nu. H hat psi equals 0. S equals K Boltzmann log omega. E equals mc squared. These are not features of any one universe. These are the laws under which Platonia is structured. Where do the laws come from? This is not a question Barbour's program answers. It is not a question the Wheeler-DeWitt equation answers. It is not a question shape dynamics answers. Each of these frameworks is written in the language of certain mathematical relationships: the principle of least action, the canonical quantization procedure, the conformal symmetry. These relationships are not derived from within Platonia. They are the conditions under which Platonia is even defined. The materialist who is happy to say Platonia just exists with all its structure must also be happy to say, and so do all the laws that give it that structure, written in the precise mathematical language that just happens to permit conscious observers to discover them. This is the design argument in its sharpest form. Not the design of a particular configuration, the design of the law space within which configurations live. Consider what would have to be the case for the materialist position be honestly maintained. Either the laws, the mathematical structure of Platonia, including the action, the symmetry, the measure, the relationships between observables, are necessary in the strict logical sense, such that no other set of laws is possible, or they are contingent, in which case they require an explanation external to themselves. The first option is not supported by mathematics. There is no proof that the action defining our particular Platonia is the only logically possible action. Hundreds of alternative actions have been written down in the theoretical physics literature, each leading to a different configuration space with different dynamics. The materialist who claims necessity cannot point to a proof. The second option, contingency, leads, by the principle of sufficient reason, to a cause external to the law structure itself. Something specifies which mathematics is realized. Something gives the action its form. Something, in other words, configures the configuration space. The candidate this argument points toward has, on the evidence we have collected, the following properties. It exists prior to Platonia, in the sense that it is the ground of Platonia's structure, not a member of it. It possesses the kind of capacity that selects one possibility from many, what we ordinarily call will. It possesses the kind of precision that yields the exact mathematical form that supports observers, what we ordinarily call knowledge. It possesses the kind of power required to make a configuration space and impose its structure, what we ordinarily call power. These are not new attributes. They are the attributes that classical theism has assigned to an intelligent cause for 2.5 millennia. What does it mean that the most refined attempt in modern physics to remove an intelligent cause by removing time arrives, when pressed for the explanation of its own structure, at the very attributes the intelligent cause was supposed to have? The fifth weight, and we will move quickly here because it is the most often misunderstood, is the question of whether eternalism and Platonia actually undermines free will, agency, and moral responsibility, as is sometimes claimed in popular materialist commentary. The argument runs, if all nows exist, then your choices are not real, because what you are about to do is already a feature of some now in Platonia. Therefore, freedom is illusion, and responsibility is illusion, and morality is illusion. This argument confuses metaphysical structure with causal explanation. The now in Platonia in which you choose is a now in which a particular configuration of your brain, your environment, and the records pointing to your reasons are all present together. The choice is not eliminated by being part of a static landscape. The choice is what makes that now the configuration it is. To say you did not really choose because the now is already there is like saying you did not really compose that sentence because the sentence is already written. The composition is the existence of the sentence. The choice is the existence of the configuration in which the choice is made. The eternalist who claims this argument is making a more basic error. He is confusing the externalist perspective of looking at Platonia from outside with the internalist perspective of being a part of one of its nows. From outside, every choice has already been made. But that already is not a temporal already. It is the mode of being of Platonia itself. It does not remove the choice. It removes the temporal language we use to describe choosing. If anything, Platonia heightens the question of responsibility rather than removing it. In a flow of time universe, your choices are at least partly excused by the fact that you did not know what was coming. In Platonia, every now in which you choose includes all the records, all the consequences, all the relations, and you are the configuration that chose. There is no before in which you were ignorant of what would follow. The choice is present, complete, with all its implications visible. What does it mean that the materialist who deploys Platonia against free will has not understood that Platonia, on its own terms, makes the moral weight of each choice heavier, not lighter? The sixth and final weight is the simplest. It is the one that the materialist most often refuses to acknowledge. Even if you grant every philosophical move that the materialist makes, even if Platonia is brute fact, even if the Janus Point removes the special initial condition, even if a measure can be defined that diffuses the Boltzmann brain problem, you have not solved the deepest question. Why is there a Platonia at all? This is the question Leibniz asked 3 centuries ago in his Discourse on Metaphysics. Why is there something rather than nothing? The materialist has redefined something. He has redefined it as a particular static configuration space. He has not answered the question. He has only relocated the something whose existence requires explanation. The cosmological argument, in its mature form, is not refuted by Platonia. It is sharpened by Platonia. Because Platonia is not, on Barbour's reading, the kind of thing that brings itself into existence. Platonia just is. The mathematics of Platonia just is. The action that defines Platonia just is. And the fact that any of these things is, rather than nothing, that is the question. The first cause argument has always been not about what happened a long time ago. It has always been about why there is a foundation at all. Whether the foundation is a four-dimensional space-time, a multiverse, or a timeless configuration space, the question recurs. The foundation cannot be its own foundation. Either it is necessary in a strict logical sense, and nothing in mathematics has shown that any of the foundations seriously proposed in physics meet this bar, or it is contingent. If contingent, there is a reason external to it for why it is rather than is not. The evidence we have surveyed, the Bloch universe, the Wheeler-DeWitt equation, Platonia, the time capsules, shape dynamics, the Janus point, the past hypothesis, the precise mathematical form of the action, the unsolved problem of the measure on configuration space, does not, on examination, point toward a self-sufficient cosmos. It points toward an extraordinarily structured, finely specified, mathematically articulated reality whose own existence is contingent on something external to it. Something selected this Platonia rather than another. Something specified the action. Something gave the configuration space its complexity function with its global minimum at the Janus point. Something fixed the initial conditions whose improbability Penrose tried to compute. Something, in other words, with the attributes of an intelligent cause, power, knowledge, will, and existence prior to and independent of the structure being explained. This is the rational position. It is not the position that says we may never know. It is not the position that asserts agnosticism in the face of the evidence. It is the position that follows the evidence to where the evidence actually leads. The materialist will object. He will say that this conclusion smuggles in religious commitments. It does not. The conclusion follows from a strictly philosophical principle, the principle of sufficient reason, applied honestly to a physical theory taken at its own word. If Platonia exists, and if its existence is contingent on a specifying structure, then there is something external to Platonia that specifies it. The attributes of that external something, what it must be to do what it does, are what theism has always assigned to its primary cause. We have followed the evidence. The evidence does not refute theism. The evidence requires it. Let me bring this exploration to a close. We began with Einstein's letter to the family of Michele Besso, in which he called the distinction between past, present, and future an illusion. We have travelled in three parts, from his Bloch universe, through the Wheeler-DeWitt frozen formalism, into Julian Barbour's Platonia and its time capsules, across shape dynamics and the Janus Point cosmology, alongside the relational and thermal time proposals of Rovelli, Page and Wootters, and finally to the great improbability of the past hypothesis. Roger Penrose's 1 part in 10 to the 10 to the 123rd. We have examined the claim that, taken together, these results show the universe is self-sufficient and requires no cause. We have weighed the claim against the structure of Platonia itself. We have seen that the structure is not self-existent, but contingent. We have seen that the Janus point does not remove fine-tuning, but relocates it. We have seen that the multiverse move on Platonia depends on a measure no one knows how to define. We have seen that the very laws that make Platonia what it is are contingent and call out for an explanation external to them. The evidence does not point to a universe that explains itself. It points to a universe whose own structure cries out for explanation. A configuration space precisely shaped, finely tuned, internally consistent, mathematically articulate, and ontologically contingent. The kind of explanation it calls for has, by the form of the argument, 3 attributes. Power, because something must give it being. Knowledge, because something must give it precisely the form it has. Will, because something must select this configuration space from the infinite possible alternatives. These are the attributes of an intelligent cause, not the cause of a moment of becoming, for there is no becoming in Platonia. The cause of the existence of Platonia itself. This is the part that stays with me. Not the strangeness, the precision. A configuration space of unfathomable complexity. An action of exact mathematical form. A complexity function with a single global minimum, positioned in just the way needed to give rise to records, memories, observers. A past hypothesis with an improbability whose exponent cannot be written in human notation. None of this looks like accident. All of it looks like design. The universe is not what materialism told us it was. It is not the random flicker of mindless matter. It is a static, structured, mathematically articulate reality, whose existence, whether you call it a block of space-time, a wave functional of a configuration space, or a library of nows, depends on a cause that, by every logical requirement, possesses power, knowledge, and will. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. The next time you remember something, your childhood, your wedding day, the face of someone you have loved, consider what Barbour has asked us to consider. That memory may not be the trace of a moment that was. It may be the present feature of a now that is. Behind the now, behind the Platonia in which it sits, behind every action and law and structure that makes this configuration even possible, there stands what must stand for any of it to be at all. An intelligent cause, eternal, uncaused, possessing the power to specify what exists and the knowledge to specify it precisely. Not a part of the library, the author of it. Sleep well tonight, resting inside a now that, however still it may be, is held in being by something that is not still, by a cause whose existence does not depend on time, because time was its first creation. Good night.